In the last nugget, we saw how analog voice waves can convert to digital numbers, just zeros and ones being sent over a wire. Now, by doing that, we've solved the distance problem. Remember, analog signals would have to be regenerated and repeated every certain amount of distance and to extend the signal further, but that would introduce more line noise and white noise on the line, and that would end up causing major quality problems over long distances. So by converting them to ones and zeros, you can send ones and zeros as far as any one can send without any need for white noise or anything like that, because it's just ones and zeros. Either you send them or you don't. Now we have to conquer the second problem that we had with analog connections, and that was the amount of wires. How do you send multiple calls over fewer wires than the analog connection took? Well, that'll be what we talk about with time division multiplexing. We'll then look at the specifics of T1 and E1 CAS and CCS connections. Now, if you come from the data world like me, CAS and CCS, when you think of them, you think of, okay, I either get 24 channels for my data or I get 23. Well, duh, why not always go with the 24 to get the bonus channel? Well, in the voice world, that's not always so. That's actually most of the time a false assumption to just say go for the bonus channel. So we'll talk all about that, difference between CAS and CCS and ISDN connections. Well, let's start off with the magic system that allows you to send multiple phone calls over a single connection. That is known as time division multiplexing, or TDM. Now, TDM carries multiple conversations over a 4-wire path rather than each conversation taking 2 wires like it did in the analog world. It does this by building a larger connection through these channels known as DS0s. Now, some of this may be review for you. Even in the data world or the voice world, you might have heard of DS0. It's a single channel, 64 kilobits per second of bandwidth per DS0. And that's when we hear of our T1 lines and E1 lines, we say, oh, well, T1 is 24 channels or 24 DS0s all bundled together. So 24 64 kilobits per second connections all spliced together into one line. Now, when you build one of these connections, each one of those DS0s is given a unique time slot to transmit. That's where time division multiplexing gets its name. How are you able to send multiple calls over single connections or a 4-wire path? Well, the way it does that is by assigning a specific time slot to each one of those DS0 channels. So for example, let me grab my pen here. Where's my pen? For example, we've got this little line of time slots coming out. Here's our conversation 1. It would have a specific time slot. Now, I'm not going to get into the numbers, but let's just say this is from 0 to 32 milliseconds or something like that. Then time slot 2 starts from 33 to 64 milliseconds, and time slot 3 starts from 65, and so on and so on. Each one is given its own little time slot to send, whether or not it has data to send. You see this little blank right here? That's our DS02. Now, or sorry, DS02. That's the time slot. Now, we have actually 4 calls that are going out, or I should say 3 calls, but as of right now, DS02 disconnected, so there's no data being sent. Regardless of whether it has data, it still gets its time slot in which it can transmit. It just doesn't send anything. Best way I can visualize this is, I don't know if you've ever gone to Disneyland on a non-crowded day. It's the greatest day in the world because you can just get on all the roller coasters without standing in these long lines. Well, if you've ever seen them, you have these roller coasters, and the one I'm thinking of, if you've been there, is the Haunted Mansion. You ever seen that one? Where you're kind of going through this haunted mansion, and then you come to this place where you get on this kind of conveyor belt of chairs. Now, if there's people to get into the chairs, then they'll get in and go through the haunted mansion. But if not, then you'll just have this blank chair, and that's what me and my wife had. We had this blank chair in front of and behind us, which was a time slot where there was no people to satisfy it. So it was just a blank chair that went through the whole haunted mansion without any people. In the same sense, you get all these time slots with data that goes in them, whether there's data there or not. It's the specific time that separates them. That's why we call it time division multiplexing. Common TDM groups, or DS0 groups, is a T1 line, which is 24 DS0s, and an E1 line, which is 32 DS0s. Now, Just a moment ago, I mentioned E1 was 30 DS0s because it's thinking with a data mindset. E1 is used in Europe, whereas, I should say E1 is used all over the world except for the United States, Canada, and Japan, and a few other regions that use T1 lines. E1 connections give you 2 channels of signaling. It's actually channel 1 and channel 16, and we'll get into that more later. So really you have 30 channels that you can use for actual data, the 30 conveyor belt channels that you can put data in. So before we move on, let me emphasize again that TDM does solve the problem of sending multiple conversations over a single 4-wire path. It does that by allocating each conversation a specific slot of time. If we're bundling them into a T1 connection, we'll have 24 unique time slots where it says, okay, now's your chance, send it now. And we can send our digital ones and zeros for a specific conversation during that time slot. The second area we have to conquer when we move into the digital realm is signaling. In the analog world, the signals were electric frequencies. And you might think back to the analog signaling nugget where I talked about how when we sent dial tone, it was a specific hertz of electrical signal. Or when we push buttons on our telephone keypad, you hear the beep, 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 beep. You know, all the different beeping noises is dual tone multi-frequency, which actually playing at 2 different electrical frequencies that we recognize as tones at the same time, and that's what lets the carrier pinpoint what digits you're actually dialing. Well, in the digital worlds, we don't have electrical signals and waveforms and hertz and things like that. We just have ones and zeros, ons and off. So we have to have a way to accommodate signaling, and our ways is how I started this whole nugget, talking about channel associated signaling, or CAS, or common channel signaling, or CCS. 2 different ways to handle signaling in the digital realm. Now, before I jump into CAS, I have to admit to you that when I was in the data world, before I got into voice over IP, when I talked about CAS or CCS signaling, or I guess in the data world, we think of CCS as ISDN. That's the only thing that would be CCS is ISDN connection. I would always just think, boring. Hello. Why do I need to know? Okay, yes, CAS is raw bit signaling. It steals bits. Okay, blah, whatever. Why do I need to know that? Well, you don't really in the data world. Okay, maybe if you really are interested, it'd be one of those who wants to be a millionaire questions kind of thing of how does CAS or CCS work. But really, you don't need to know it to set it up or to do anything like that. You just plug in your connections and type your command. But in the voice world, it's pretty critical to know how this works because we need to know how signaling is being communicated. And if signaling isn't passed, we need to know where to start looking. So, when we're thinking about T1 environments, which is the United States, Canada, Japan, those major areas, and some of other areas still use T1s as well, or use T1s, CAS in a T1 environment is known as robbed bit signaling, or RBS, robbed bit signaling. Keep that one in mind because I think that is the best description of what this does. Here's the technical nitty-gritty of it. The least significant bit in every 6th frame is signaling. That's one of those ones you have to, okay, pause the video, think, okay, what did he just say? I said the least significant bit in every 6th frame is signaling. So, when we're talking about T1s, we have, I guess, what you could call mega frames, or I guess the technical term is extended super frames. That is a T1 frame which has a bunch of these smaller frames in each one. Now remember, think back, time division multiplexing, or TDM, allows you to send multiple conversations on a single circuit by just assigning them each time slots. Well, here's our time slots. Here's our first time slot. We send our first DS0 channel digital stuff. We'll say, 00101, whatever digital numbers are in there. Then we have our second time slot right here. Second DS0, third DS0, we got our ones and zeros and so on. Fourth, this goes all the way to, you see my ... all the way up to what? 24, because there's 24 DS0s that are bundled together into T1. Sending those 24 frames all at once is one T1 frame. So when I say frame 1, you can think of it in multiple ways. It's frame 1 of each one of these DS0s, or you can think of it as the first T1 frame that's sent, which is a whole bunch of frames bundled into one. Now at the very, very front of that, and I'll show you this later, is actually a little framing bit. Just like we have like a header on our packets, or at the end of the data link frame in the data world, we had our CRC or frame check sequence or cyclical redundancy check that we just add onto the front. We have a little framing bit at the front of these T1 frames as well. Again, more on that later. I just want to emphasize this is a frame. So as we go down, you send your frame 2, frame 3, frame 4, frame 5, frame 6. The least significant bit, that guy, right there. This one, this one, this one. In every single one of those DS0s is reserved for signaling. So when the receiving side gets all those together, notice I just put my little S here to signify this is a signaling frame. When the receiving side gets it, it puts all those back together and says, okay, I've got, at least for the first 4 DS0s, 0, 0, 0, 0. There's my first signaling bits that I have. Then it goes on, frame 7, frame 8, frame 9, frame 10, frame 11, frame 12, signaling. So the last bit of the 12th frame will all be signaling. 18th frame, 24th frame, 30th frame, so on and so forth. Every 6th frame, the last bit is signaling, and the receiving and sending sides can actually take all those bits and put them back together and start getting signals like off hook, on hook, dial digits, even caller ID information can be reassembled from that. Now, there's a consideration of that. Think of the name, robbed bit signaling. We are robbing one bit from every 6th frame to use for signaling. Now wait a sec, think back with the last nugget. We talked about the Nyquist theorem and how you have to have 8 bits to regenerate human voice and that kind of thing. And we've robbed our 8th bit for signaling. So for every 6th frame, you only have 7 bits that you can use for signaling purposes. For voice, it's not that bad. Taking a bit out of every 6th frame does not, and I'll say it as the textbooks would, does not significantly impact voice in a noticeable way. You got that? So stealing 1 bit out of every 6th frame, yes, it takes the quality of your voice down. But it's not down so much that somebody on the phone, like you or I listening to a phone conversation, would be able to go, whoa, this is definitely a CAS or rob bit signaling connection, because I can tell your voice is just kind of garbly. And no, it's nothing like that. However, I will say for data connections, if you're sending data over one of those DS0s, like a fax signal, that can start hammering some of the quality, and you're going to need a lower speed fax signal because it's going to drop your quality down that is expected to be there for data connections. Okay, now I think I jumped a little bit ahead of myself on that last slide, so let me just hit these high points again. Every 6th frame in T1 CAS is missing a bit, which is known as raw bit signaling. That does degrade the quality, but not noticeably for the human ear. For data connections, though, it can be a consideration. T1 sends a giganto. That's the technical term. A giganto T1 frame of 193 bits at a time. So a T1 frame, and this is what I was saying before, a T1 frame is actually all 24 DS0 channels with a little framing bit on the end. Now, this helps explain a little something. I don't know if you've ever done this like me. Have you ever thought about a T1 line and you think, okay, let me pull up a calculator here. If I've got 24 channels, right, and each channel, I'll multiply this, has 64 kilobits per second, right? So you've got 24 DS0s, each channel is 64 kilobits per second. That gives me 1536 kilobits per second, or you think of 1.536. But then wait a sec. Why does everybody say a T1 line is not? They don't say a T1 is 1.36. I say a T1 line is 1.544 megabits per second. That's always the speed. Where's this? If you just add the bandwidth of all the DS0s together, you get 1.536. Where's the extra little smidge come in there? That's the framing bit. Every single one of these giganto frame has 1 bit on the end of it, which adds all up, which that's what ends up giving you the 1.544 megabits per second is including that extra framing bit. So When you're sending T1 frames, there are actually two framing types that are out there. Superframe, and if you've come from the data world, this is where it gets familiar, because you go, oh yes, this is something I have to configure. I have to type in framing SF or framing ESF, which is extended superframe. Superframe sends 12 T1 frames at a time. So, this is a T1 frame. If I configure my interface for superframe, I'm going to send 1 through 12 at a time, and that will be considered one, I guess you could call it one big frame that is being sent. It's a superframe, which is a whole bunch of them. Now that gives me A and B signaling bits in each one of these. Now, I know you're thinking, well, I thought, A and B, where did this come from? Remember, every sixth frame is signaling with round bit signaling. If you're using superframe, it will combine together the signaling from the 6th frame and the 12th frame, and then it sends 12 more, and then you'll have a 6th frame and a 12th frame, then it sends 12 more. 12 T1 frames sent at a time. So your signaling is what's known as A and B bits. So for example, my signaling for the first DS0 for the 6th frame might be 0, 1 and that would be for 6th and 12th frame. This is 0 is my 6th, 1 is my 12th, because you get 1 bit. And then, maybe for the 18th and 24th frame, I'd have a 1, 0. Each one of those means something. When I put those back together, that means, oh, the phone is off hook, or the phone is on hook, or the phone is ringing, or, if I had a 1, 1, a 0, 0, all of them mean something. Now, I can't just lay it out and say, okay, well, if I'm using superframe, 0, 1 always means the phone is on hook, and 0, 0 means it's off hook, and 1, 0 means it's ringing. You can't say that, because there's different types of signaling that are out there. And I know, this is where it's starting to go, huh? What are you talking about? CAS is a signaling type, right? CAS, or robbed bit signaling, says steal the last bit of every 6th frame. That's what CAS says, or robbed bit signaling says. Superframe, an extended superframe, says how many of these T1 frames we send at a time. With superframe, I only send 12 at a time. With extended superframe, I send 24 of them at a time. So I have what's known as A, B, C, D signaling bits. So for every group of frames that I send, I have 0001, 0010, I have all these different bits that can mean different things. So I can tell you the modern world out there uses extended superframe. Superframe is all but obsolete. Just about everybody in every carrier uses extended superframe. So let me go back to what I was saying just a moment ago. I can't say what each of these mean. I can't say a 0001 means the phone is on hook, or if I'm using superframe, I can't say 01 means on hook, because it depends on what kind of signaling I'm using. This is a type of framing, not a type of signaling. This is a style of T1 connection, not really a type of signaling, or a way to configure your T1 and how it uses its DS0. The type of signaling we have yet to talk about. That's things like FXO ground start, FXO loop start, FXS ground start, ENM wing start. There's all kinds of different signaling that are out there, and we'll talk about that in a moment. And that is what defines what these mean. For example, if I've got a router connected to a, well, I shouldn't even be talking routers yet, right? Hang on, routers, no such thing as a router yet. I have a PBX system connected to the PSTN cloud. Here's my PSTN. Now, if they're using FXO, we'll say ground start signaling on the PSTN, I'm going to configure my T1 CAS line to do the same thing. And based on FXO ground start signaling, now I can say, and I can look it up in a reference book, I can say, oh, well, with FXO ground start, 0001 is on hook, 0010 is off hook. I can say all those things because that's what the signaling standard dictates. Depending on what signaling standard you use, that's where you combine all these bits together, if you're using extended superframe, into a legible message of this is what this represents. That represents a dial digit 9, whatever. Now before we dig too deep in this, hang on, take a step back, breathe deep. All we're talking about is the signaling, the new way to send signaling over a digital line. In the analog world, we had signaling that was sent using the electric waveforms. Like dial tone would be, that steady hum you hear is just an electric signal they send. When you hit the button on the phone, the beep, that's just an electric signal that's sent. So all of these things that we're used to in the analog world have to be replicated or regenerated in the digital world using zeros and ones. That's what those signaling bits are there for, is to regenerate all those dial tones and all those different types of signals using ones and zeros. So robbed bit signaling is how we do it in the T1 CAS world. E1 CAS, I almost say there's no such thing. There is, but when I think of E1 CAS, I don't really think of any benefits. Like in T1, the reason robbed bit signaling is so great is because, get my spreadsheet out of there. The reason it's so great is because I now have 24 DS0s. You know, each one of those conversations, I can use every single one of those 24 DS0s for voice. I don't have to dedicate one of those channels and say, that is my signaling channel, I can't use it for voice. I just rob a bit out of every sixth frame and put them all together, and that can help me regenerate the signaling. So I think with T1, wow, what a benefit. I get a bonus channel that if I used CCS, which will be the next signaling type, I couldn't get that because one of the channels would be completely dedicated to nothing but signaling, and I couldn't use it for voice. So you can see with T1, total benefit, I can use 24 channels instead of 23 channels for voice. With E1 CAS, you don't get the benefit. E1 CAS is pretty rare because you sacrifice quite a few things, but don't get any return on your investment. For example, if with T1, I at least got the 24th channel. You know, normally I can only use 23, but now I can use 24, like I mentioned. With E1, I don't get it, meaning 32 channels I get in E1. Channel 1 is always dedicated to framing. Remember on T1 that bit I added at the very end of every single Giganto T1 frame? That was framing in T1. Well, when E1 came out, they said, well, let's dedicate the first DS0 channel, the whole first DS0, to nothing but framing. So I lose one channel there. And then channel 17 is always dedicated to signaling. It doesn't matter if I'm using CAS or CCS, that 17th channel is always signaling. I think I said channel 16 a little earlier in here. Channel 16, I guess you could call that the time slot. Remember in Cisco, everything starts counting from 0. So if you count from 0, it's the 16th time slot or 16th channel. If you count from 1, it's going to be the 17th channel. That's always going to be dedicated to the signaling and E1 connections. So even if I'm using E1 CAS, which says, you know, I'm trying to, you know, steal bits, if you will, in my CAS mindset. Well, in E1, I don't really gain any benefits. I don't get an extra channel. The 17th channel is always dedicated to signaling. It does not do rob bit signaling. And let me just emphasize that. Rob bit signaling. Circle, cross. There is no robbed bit signaling in E1 because each one of those DS0s never lose bits since this is always dedicated to signaling. So you might wonder, as I did, when I looked at this, well, you know, I even put a bullet here. E1 CAS is counterintuitive. It's called CAS since each time slot signal matches to a voice channel. When I first saw this, I thought, well, you know, why do you even call it CAS, channel associated signaling? Because you're not associating the signal, you know, with each one of these channels that you've dedicated. You have a common channel. There's one channel dedicated to signaling, so why do you call this CAS? Well, the reason why is because it uses the same standard of signaling that T1 does. Meaning, if I were to grab the first frame from this DS0, every frame in that DS0 is 8 bits. The first 4 bits are dedicated to DS0, well, I guess you could say DS02, which is going to be our first voice channel. The second 4 bits are dedicated to DS032, the last voice channel. Now, as the next frame that comes across, the first 4 bits will be dedicated to DS03. The last 4 bits will be dedicated to DS031. It kind of counts its way down and meets in the middle. So it uses the same signaling type, meaning the same ABCD, you got ABCD, as extended superframe does in T1 line, so they're totally compatible. I can bridge an E1 connection to a T1 without, transferring signaling or anything like that. The reason they call this common channel signaling is because it's using the same kind of signaling that T1 does with its raw bit signaling. It's just dedicated in its own channel. Because of that, most E1 carriers don't use CAS because there are benefits that you get in using CCS, meaning dedicated signaling channel, common channel signaling, that you can't get with CAS. So with E1, they're saying, well, why would I do this if I can use CCS and get more benefits and I'm not really gaining or losing channels whichever way I go? So the only reason E1 CAS is around, and I'll say this in my opinion, is because it's compatible with T1. And if you need to bridge E1 to T1 connections, maybe there's some international divide there, then you can do that using E1 CAS. So now let's talk about the other method of bundling our channels together on a T1 or E1 connection, and that is CCS. In a way, CCS is so much simpler than CAS because we don't need to know all these facts and figures of, the least significant or 8th bit of every 6th frame goes to signaling, and that's the A bit and the B bit, and extended frame is, blah. Throw that all out the window because CCS dedicates a signaling channel in both E1 and T1 lines. Now in E1, that's no change, right? Because in E1 CAS, the 17th frame is always signaling. Well, in E1 CCS, guess what? 17th frame is also signaling. It's just that it's using a signaling protocol rather than just 4 bits per channel. Now remember, when we had our T1 or raw bit signaling connection, we were able to put together, 6th frame, 12th frame, 18th frame, 24th frame with our extended super frame. We got 4 bits. I put it to 4 bits, 0, 1, 0, 1, or something like that we could send with signaling. Now, if you only have 4 bits per frame to put signaling together, there's not that much that you can send. I mean, you can send on hook, off hook, called number information, basic stuff, but there's a lot of different features in the PBX realm that we need to transfer signaling information for. I mean, some of them are complex features like integrating with PCs in the digital world. Some of them are simple features. Some of them are even proprietary features. You can't really get into those if you use CAS connections because the 4 bits doesn't give you enough flexibility to send those kind of messages. You've got 4 bits, which represents a number, right? You can't really send, do this or do that. It's just a number, and the two sides will interpret that number to say, well, that means it's ringing, or that means it's on hold, or that means, all of these different meanings are assigned to those numbers. Well, if you've got a channel dedicated to signaling, then you can use a signaling protocol that communicates in its own language. Now, the most common signaling protocol is ISDN. And that's why when most people think of CCS, or at least in my mind in the data world, I always think CCS equals ISDN. They are one and the same. That's what it is. And in the data world, that's true. That's correct because we don't really think of anything else other than ISDN for CCS. But in the PBX world and in the voice over IP world, that's not true. Most of the time, people will use the signaling protocol Q931, which can send complex signaling messages. It doesn't use bits anymore. It uses hexadecimal. It uses text messages. It uses all kinds of things. It's a protocol. It's a signaling protocol where you can put even your own proprietary signaling messages, which many PBX vendors did. If I bought an Avaya PBX on both ends, I could get proprietary cool features between those two, and ISDN's Q931 could send that. But there are other signaling protocols out there. For example, there's one known as SS7. SS7 you can think of as the carrier protocol of the world, meaning I've got all these central offices, right? Here's my PBX system over here, and I connect in to a PSTN central office. And that CO connects to another CO, and that CO connects to another CO, and there's this massive network all around the world of all these carrier central offices connected together through all these trunk lines. Now those trunk lines all run the signaling protocol SS7. That is what allows the carriers to have a standard, a common standard, that it doesn't matter what carrier you are, you're always using SS7 or Signaling Standard 7 to communicate between your offices, and thus we have a compatible, almost TCP/IP-like worldwide standard that phone carriers use between each other. All these phone carriers between their central offices use CCS, where they've now got a dedicated signaling channel. So if you're using T1, the drawback of using CCS is you now only have 23 channels. Here's my 23 channels of data, and that 24th channel is dedicated. It's gone. I can't use it for voice anymore. That is all signaling information. With E1 lines, there's no drawback. You don't lose a voice channel because it's the same as it was in CAS. The 17th channel, or 17th time slot, is your signaling information. Now you can see why people that use E1 lines, it's far more common to use CCS, is because if you lose a channel either way, it's better to have a signaling protocol than using those 4 bits to convey your data. So there we have it. The way that digital signaling has solved all the problems of analog. First off, by converting it to ones and zeros solves the distance problem, as I mentioned when I opened this whole nugget, talking about how you can send ones and zeros any distance without any line noise or anything getting in the way. The second problem was solved by using TDM, where I was able to now come in here and say I want to send multiple conversations over a single 4-wire path. That's time division multiplexing, which assigns each one of those conversations its own time slot. We looked at CAS signaling, which in T1 is known as robbed bit signaling because it steals bits out of every 6th frame to comprise all the signaling information that can be used to send on hook, off hook, all these different types of signals. And then we looked at E1 CAS, which doesn't really give you any benefits because it still dedicates that 17th channel for the same kind of signaling that T1 CAS uses. So T1 and E1 CCS is probably the more common one in the voice world because it is the one that allows you to send more complex signaling types, giving you more flexibility and features that you can send using signaling information than we had in the T1 and E1 CAS world, dedicating either the 17th in the E1 world time slot or the 24th time slot in the T1 world just for signaling information. I hope this has been informative for you, and I'd like to thank you for viewing.